So, welcome to the ICT for Development 2021 conference. I am one of the keynote speakers. Unfortunately, due to the present situation in Ethiopia, this conference was moved to a virtual conference. As a part of this virtual conference, I am now delivering my keynote speech in the form of a video. The title of my talk is The Contribution of Unsupervised Learning and Recursive Learning to Facilitate Joint Deployment of Unmanned Aerial Vehicles, Mobile Robots, and Sensor Networks. I am a professor at the TU Dresden and head of the Energy Lab at the Faculty of Computer Science. My research activities encompass wireless sensor network, ubiquitous computing, energy efficient computing, and stochastic processes with the focus on unsupervised learning. In February 2021, as you can see here on the slide, NASA successfully landed a rover on Mars. Included in this deployment was a small robotic helicopter equipped with some elementary cameras. And the purpose of this deployment is to study the possibility of biological life in the Mars. The rover, as you can see here, is equipped with different types of sensors and devices. For example, the MEDA component here you see includes humidity sensor, air pressure sensor, temperature sensor, and also it is capable of sensing the shape and composition of sands and stones. The rover is also able to convert carbon dioxide into oxygen, the aim being investigating the possibility of bringing microbiology on the planet. The rover itself currently it's just a prototype, but in the future the idea is to assist the rover in its sensing and investigation assignment. Currently, the helicopter leaves the robot for a few seconds to hover above or nearby and give the robot some idea about the environment. The robot, which is equipped with advanced signal processing and chemical devices, but limited in its mobility, covering only about 200 meters a day. When the helicopter is fully equipped, then it can harvest its own energy, stay longer on air, and use advanced camera and audio systems to collect relevant data about the red planet. Now imagine, in addition to these devices, we could also deploy wireless sensor networks on the ground. The wireless sensor nodes are able to sense data, communicate wirelessly, and also do some advanced in-network processing. This would enable high spatial-temporal sensing, relieve both the mobile robot and the UAV from moving a lot, so that they can save energy and use this energy for the signal processing, as well as for additional onboard chemical investigation. Of course, this type of joint deployment is not limited to Mars or outside of the Earth. Here on Earth, also, we can use this type of deployment to monitor inaccessible, dangerous, remote, or extensive environment. In fact, my team is currently engaged with this type of deployments to monitor toxic gases in industry or during a spill after some storage has some accidents, or following man-made or natural disaster. Of course, toxic gases are not the only dangers. Civil infrastructure could collapse and endanger human beings during this time, both to assess the extent of damage and to rescue people and remove danger. We may need to jointly deploy mobile robots, UAVs, as well as wireless sensor network. So here, for example, we have precision agriculture and underground mining benefiting from joint deployments. In precision agriculture, we wish to administer resources at a micro level, not at a macro uniform level, but depending on the need of micro regions. For this, we need to sample soil moisture, humidity, temperature, air pressure, and additional parameters. And then based on that, we can estimate the amount of herbicide or insecticide or fungicide one could administer. Sensor network and UAVs can also jointly work to estimate yield, both in terms of quality and quantity, to organize the whole chain of supply chain so that we can target end markets or distributions. In underground mining here, as you can see, we can deploy UAVs to search for human beings after the collapse of a mine wall or some additional infrastructure. We can also search and localize equipment and also assess danger before we send human beings into these mines. This type of joint deployment, of course, require some technological support, some of which, and I list here, occupy myself and my team at the TU Dresden in Germany. The first important aspect is to self-localize all the systems, the wireless sensor network, the mobile robots, and the UAVs, enable the mobile robots and UAVs to self-navigate in the absence of any GPS or even in the absence of any infrastructure, any reliable infrastructure. This is one of the challenges facing a joint deployment. Another important aspect, these three components should self-organize and collaborate in a seamless and dynamic fashion. For that, we need to come up with efficient self-organization algorithms, both to minimize the communication cost, to minimize end-to-end latency during wireless communication, and also assist the mobile entities to navigate through complex terrains. Another important aspect is when these three components interact, of course, cross-technology interference comes into existence, and this may deteriorate the quality of communication. A high number of packet loss will be experienced. This, in turn, will affect the coordination as well as the quality of data we wish to extract from the environment. In this case, we have to be able to establish reliable communication. And finally, of course, all the three components operate with exhaustible batteries. This needs efficient energy management or dynamic power management algorithms. So these are some of the challenges which I wish to share with you, and also give you some of our solutions for these challenges. As I said, in my team at the TU Dresden, the Energy Lab, occupies itself with some of these challenges. All our research efforts are based on practical deployment, practical observations. We collect data through prototyping and physical deployments, and then based on this statistics, we use unsupervised learning, mostly tensor decomposition, singular value decomposition, principal component analysis, and recursive filters, particularly extended Kalman filters and particle filters, to address some of the issues I listed in the previous slide. For example, in indoor localization, I'm going to show you how we collect process error and measurement errors using ultra-wideband and IMU-based sensing to enable mobile robot freely navigate in indoor environment. So one of our robots, as you can see here, is equipped with ultra-wideband technology, which receives very narrow beacons coming from strategically located receivers. And then we use this knowledge along with the process error arising from the inherent driving structure of the robot to minimize the overall localization error and enable the mobile robot freely navigate. So here you can see we have anchor nodes, ultra-wideband anchor node, which emit beacons on a regular interval. These beacons are intercepted by the mobile robot. The time of difference of arrival will be taken into account to come up with the probable location of the robot. This will be used as the measurement data, and then we take this together with the process model to localize the mobile robot. For a reference, we use highly accurate sensors, and we use this type of topology, polar topology, to estimate the angle as well as the distance covered by or traveled by the mobile robot. So to localize a process error is the following. If you plan the robot to move along a straight trajectory with a constant velocity, of course, in practice, the robot neither moves in a straight line nor at a constant velocity. So we have to model the statistics of this deviation from the targeted movement. That means here, as you can see, we have the process error. This is the error along the x-axis. That means we order the robot to cover a certain distance at a constant velocity, and then measure the deviation from the intended target. Here we plan the robot to move in a straight line, but then the final destination is deviated from this straight line. As a result, we get the y-axis error, the deviation. This one, the deviation from a constant velocity. This one, the deviation in direction. In both of them, we can establish using either the ultra-wideband sensor node or the inertial measurement unit, which is embedded in the mobile robot. Likewise, we established the measurement error, the two-dimensional measurement error, and then we feed these two errors into an extended Kalman filter and a particle filter model. And the result, we gave, this is the intended mobility of the robot, and the rate is the actual mobility of the robot. So we could minimize the error of mobility in the centimeter range. We are initially, this experiment was conducted in our laboratory, but currently investigation is undergoing to enable our mobile robots, different types of mobile robots, freely self-navigating complex environments and corridors in our faculty. In addition to self-localization, another topic of interest for us is self-organization. Self-organization means when you deploy mobile robots, mobile unmanned aerial vehicles in sensor network, they should be able to organize themselves into clusters so that interaction between the sensor network and the UAVs become less intensive. The problem is in a joint deployment, there is an upward communication, the sensor sending data to the UAV and the UAV sending commands to the sensor network. Because the UAV also requires remote controlling, even if it self-navigates, still we wish to communicate with the UAV either to disseminate command or to make sure that the UAV is executing its tasks as intended. As a result of this interaction, cross-technology interference arises. So we wish to minimize the number of nodes on the ground which interact with the UAV so that we can utilize the available channels more efficiently. So that requires self-organization, and I'm going to show you what type of self-organization algorithm we put in place to minimize the upward communication between the sensor network and the UAV. So for example, this is one of the deployments we made next to our faculty here in a wild natural environment next to a modest forest. So this sensor network should be able to cluster itself so that we can organize the sensor network into few clusters, and the child nodes will elect a cluster head in each cluster, and the cluster heads become now gateways to collect data from the ground node and deliver the data to the UAV. So if we have this type of network, the dashed line here or the dotted line indicating the existence of a direct one-hop link between the nodes, we can cluster this network in a dynamic way based on the connectivity of the nodes. Nodes which are highly interconnected should be elected cluster head, but at the same time we have to choose the cluster head so that they are well distributed in the network. If you have this type of topology, of course, it is possible to establish a binary adjacency metric which represents the topology of the network. Zeros indicating the absence of link between any two nodes. For example, between node 3 and node 1, there is no connection, but between node 1 and node 4, there is a connection, as you can see here. Node 1 and node 3, they don't have direct link, but node 1 and node 4 are connected. So the cell intersecting the C14 and C41 we'll have 1, whereas C13 and C31 is 0. So once we have this, if we square this matrix, each entry here tells you the number of 2-hop links nodes established with their neighbors. Okay, C squared means, for example, if you consider node 1, it established 1 2-hop link here and 1 2-hop link here. So there are only two 2-hop link node 1 establishes with its neighbor. If you consider node 2, for example, 2-hop link is 1 2 and 1 2 1 2. So there are 3 2-hop links interconnecting node 2 with its neighbors. If we compute the power of 3 of the adjacency matrix, then you get the number of 3-hop links nodes established with their neighbor. So if we continue doing this, we can have an idea of how interconnected nodes are with their neighbors. So what we did was we used a geometric series to calculate the number of the average number of hops nodes established with their neighbors. And this gives us an idea how important or relevant nodes are in a wireless sensor network, because we wish to pick up those highly relevant nodes and make them cluster heads so that they can interact with the UAV on behalf of their child nodes. So what we did, you can rank node according to their relevance and then now assign them as cluster heads. If we don't do any further or if we don't introduce any further criteria, the problem with this approach is that the most relevant nodes may be close to each other, in which case they are not well distributed and they may not represent the entire network very well. So we can introduce additional constraint. For example, in node, first of all, we will begin with this one. This will be cluster head. And those nodes which are 1 hop away from this node, even if they are highly relevant node, are excluded from being cluster heads. This enables us to distribute the cluster heads in the network. So this is, for example, how we assign cluster heads in the network based on their relevance and how far away they are from one another. So if you consider, for example, there is at least a 1 hop distance between two cluster heads. Of course, we are not limited to 1 hop. We can also say nodes which are 2 hops away from their neighbors are ineligible. They are not to be considered cluster heads. This creates further distance and make sure that the cluster heads are far away from one another. So in this self-organization algorithm, what we did was nodes which are relevant, highly relevant, and well interconnected in the network are considered to be cluster heads, but we introduce additional constraints to make sure that nodes, cluster heads are, there is a sufficient distance between them so that they are well distributed in the network. So during the joint deployment, we introduced this type of self-organization algorithm for the ground node to self-organize itself. Now the green nodes you see here can directly communicate on behalf of their neighbors. This one collects data from its cluster and then send it to the UAV. This one collects data on behalf of its child nodes and send it to the UAV. By so doing, we can significantly reduce the amount of uplink and downlink data which otherwise could be substantial and then creates a considerable amount of packet collision and packet loss. The nodes which are not associated here are the result of our algorithm, are by the end of the day included automatically to the nearest cluster head. Okay, another important aspect is the making the wireless link reliable. This is because, as I told you, most of the UAVs have remote controller. We interact with them. This remote controller operates in the license-free band, which is also operated or used by the wireless sensor network. As a result, there is a substantial cross-technology interference, as you can see here. The low power technology most wireless sensor networks use is the 802.15.4 standard, the IEEE 802.15.4 standard. And this standard avails 16 channels, 16 orthogonal channels, with each channel having 2 megabyte bandwidth and a 5 megahertz guard band between the channels. In the absence of a UAV, this is quite sufficient. But when the UAV or multiple UAVs operate, most of the channels are affected by the UAV's remote controller, as you can see here. This noise bar, the bigger it is, the stronger the interference coming from the UAV. So in the presence of this type of interference, is it possible for the sensor nodes to establish communication with each other and also with the UAV? So we've been studying this channel and coming up with intelligent algorithm to enable a reliable communication. So here, for example, for three different types of nodes, 1, 2, 3, we consider different channels, how many packets we can successfully transmit at a time. So you can see that the different channels have different capacities, and the profile is slightly different from node to node, even if they were affected by one and the same UAV. This is because the physical placement of the sensor nodes also has some contribution. So we try to model the packet successful arrival and loss as a serial process, and try to use or estimate the stability of link, the duration of stability of this link. And we use this information to estimate how many packets we can successfully transmit. When the average link quality is bad, then the nodes should refrain from attempting to sieve the medium, and then we can switch off important components, particularly the radio component, to save energy. So what we did is, here is a pattern. For example, the yellow signifies the transmission of packets. The orange bar signifies the inter-packet interval. This interval is needed for a node to switch modes between transmission and receiving, because each successful transmission of a packet has to be confirmed by the arrival of an acknowledgement, and for that the node should switch always between receiving and transmitting. So in an ideal case where there is no packet loss, given this much time and a packet length of this one, we can successfully transmit any number of packets in the ideal and in the absence of any interference. But of course, because of interference, there would be packet loss, so n is much smaller, or the number of packets we transmit is much smaller than this n. So what we do, taking the statistics of successfully and successively transmitted and successively lost packets, this one, from this we get the number of packets which are lost and received in succession. We try to use the Poisson process to estimate the number of packets that can be transmitted in succession, or the number of packets that can be lost in succession. And we use these statistics to estimate not only the long-term channel state, which can be used to estimate the flight time, the flight duration of the UAV, but also the short-term channel state, so that we can define dynamic sleep management for different components of the UAV, as well as the sensor nodes can be switched off. Some mathematical expression to show you how we arrived at the Poisson process. So here we have estimated, this is the practical, experimentally observed statistics of the number of packets that are lost in succession, which enables you to estimate the short-term link quality. And this is how we try to model using the Poisson process. And this is how we establish the short-term and long-term statistics. So in this talk, I gave you an idea regarding the opportunities that can be obtained by joint deployment of UAVs, mobile robots, and wireless sensor networks to monitor remote, inaccessible, dangerous, or extensive places. Of course, this type of joint deployment requires coordination, self-organization, self-localization, and power management strategies. And I have showed you how, with practical deployment and practical observation, we collected statistics. And based on these statistics, we were able to propose models for link quality estimation, flight duration estimation, for self-organization, and self-navigation. I hope this talk encourages you to investigate some of the problem I introduced here more closely and come up with interesting ideas. If you are interested to get in touch, feel free to contact me. All our papers and some of the data we collected are available on our website on ResearchGate. Feel free to access and read them. Hopefully, we can get in touch and enlarge some of the solutions which are proposed in this talk. Thank you for listening. And for now, bye from me.